Well, here we are at the end of a long week. Hope you're doing well. Thought we'd do an investigation, no homework that connected with it. Just want to explore some ideas with you. Today we're going to be looking at graphing functions, and we've had some good conversations about functions. And we're going to look at what is investigation 9. So I9, graphing functions, what you're looking at here is a function. We also have some James Taylor in the background playing for you. This will mean I can't post this on YouTube, but enjoy. Y equals 2x. So we're going to reestablish some ideas that I know we're already familiar with. One is we're going to make a little T-chart. I know you've seen these before, where the x always goes on the left and the y always goes on the right, and we'll get to the right in a second. We know there's some words we associate with our x coordinates. One of them is input. Another set of words the x relates to is independent. And then might be a new one or newer to us is something called domain. And these words can somewhat be used interchangeably, but we know that they have like a pair that goes with them. So if x is the input and we focus on our y, the y is, you know it, the output. If we say that x is the independent value, we say that y is the dependent value. And we've talked before why that makes sense, right? We always input for the x, which puts out or outputs the y. We can put in anything we want independently into the x, but whatever the y becomes is absolutely dependent. Now, this last word of domain for x and its correlative word for the y is range. And I got to tell you, it doesn't make much, not human sense, but we don't use those words in the same ways in our regular language. However, if we were to focus in on this function, and we were going to choose some inputs for our x, let's go with 0, 1, 2, 3, and for good measure, let's throw in a negative 1. What we do is we would plug in, we would substitute in for the x value. We were just dealing with this in yesterday's lesson. So we'd take that y equals 2x and we'd say, okay, so y equals 2 times 0, which would be 0. Or then when we input the x, we'd say y equals 2 times 1, therefore y is equal to 2. When the independent value is 2, then the dependent value would be, 4. If the domain was 3, then the range would be 6. And let's deal with our negative 1 too. So negative 1 times 2 is clearly negative 2. Now, you know what we do with these things. If not, we'll just look at the lesson title. We're going to graph them. Well, how do we graph this? Well, remember, these are all coordinates. So this 0, 0 is simply 0, 0. Or this one, we've got a 1 and a 2. And so on. And so on, and so on, and so on. So we're creating coordinates when we make these XY tables. And what do we do with coordinates? Well, those we're going to graph. Now, we had some graphing experiences this year, and I just want to always remind you, look, always ruler, always on the lines provided on your graph sheet. Always, always, always. So I'm going to flip to this next page. I don't have a lot of control on coordinate planes because it's kind of like an image that comes up that I can write on it. Notice how I've placed my first arrow. Here's my second arrow. Here's my third, and here's my fourth. Another thing I've always encouraged us to do is let's mark our 5Zs. So at every little 5Z point, again, that could be the 5Zs or 10Zs, but let's just keep it at the 5Zs. It doesn't need to be super big. About this size would be more than enough, right? Notice how we're not putting every conceivable number down. We don't need that. Our brain doesn't. We see the 5Zs, we'll go with it. Now we're going to plug in these coordinates that we've done. Now you're looking at them on your thing, and I'd have to rewrite them to bring it back. So I wrote them on a piece of paper here. We know we had 0, 0. Well, that's the origin, so I'll mark that. We had 1, 2. Go ahead and mark that. Good. Is it here? It should be. Okay. How about 2, 4? Mark it. Okay, good. Hopefully. And then 3, 6. Yeah, you should have marked there. Good. And then we've got our negative 1. So remember, on the x-axis is negative 1. That's back to the left. And then down 2. Boom. Now, hopefully you see that all these points are forming up to be a line. And so we would then take our trusty ruler and we would draw a line and put arrows. Now, unfortunately, you can't put a ruler down on an iPad because it won't let me write. I've tried things. If you have any great ideas for this, that would be great. That's the best I can do. Yours should look sharp, 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 right? So yeah, we've done this before. Y equals 2x is a linear function, therefore it graphs as a line. We got more to explore though. So we can look at certain real world situations, and those are functions as well. Does anybody recognize what this is? Okay, go ahead. Well done. The formula for perimeter of a square. So if we name our input to be the S, which represents side length, and the P is our perimeter, and we throw in certain values for the S, and again, we're not talking about the sides. We know there's 4 sides. It's a square. But we're talking about length, so side length. So what if I had a side length of 1? 1 centimeter or 1 mile, doesn't really matter. Oh, or a side length of 2, or a side length of 3. Can I figure out the perimeters? Yeah, because I would just plug it in, right? I'd plug in 1 for the S, and I'd know that my perimeter would be 4. It could be 4 miles, 4 feet, whatever the case. If my side length was 2, then my perimeter would be 8. And if my side length was 3, then my perimeter would be 12. Now let me ask you something. Would it be okay for me to put -1 as my input? We were able to do it before. Can I do it now? And hopefully you're saying, no, you cannot do that now. And the reason why is because side length is a distance. And we know that distance or side length can never be negative. And let's write that down. So yeah, if we're just dealing with numbers like y equals 2x, yeah, things could be negative. However, in the real world, distance cannot be negative. And because this P equals 4S models a real world situation, we're not going to choose any negative inputs. Remember what we've created here. We've created coordinates 1, 4, 2, 8, and 3, 12. And what do you think we're going to do now? Yeah, I bet you know. But here's the thing. I don't need a full coordinate. So what we're going to draw is just going to be one quadrant only. Can you tell me which quadrant that would be? Yeah, well done. It's called quadrant 1, or the first quadrant. So only the first quadrant. Now you're going to draw it on, space down below. I'm going to go to a new page. Now remember, I'm limited. So what I can choose from either white paper, which is what you've seen most often. I can choose from graph paper, which is what this is, or I can choose from a coordinate grid. Because I don't want any of the other quadrants, I went with the graph paper, and I drew a nice, as straight as I could without a ruler. You've got a ruler. And again, about that size would be good. Don't make it really small. We've seen that before. Kind of model this as much as you can. Now, here's the thing. We have named that our side lengths are input. That's our x-axis. So, and our perimeter goes up to, as far as we saw, was 12. So I'll name my 5z's here on my y-axis at 5 and 10. And I'm actually going to name these just to kind of help me with this real world situation. And the reason why I'm going to name them is because I'm going to make slightly different decisions on my x-axis, on my side lengths, because I only went up to 4, right? So there's going to be my 1, there's going to be my 2, there's going to be my 3, and that's all I needed, right? I didn't go up to 4. I lied. Sorry. So are you allowed to make different decisions for your X than for your Y? Yeah, absolutely. But they have to be uniform within themselves, the spacing and such. So in the bottom, I've kind of named that every 2 boxes is equal to 1. Because it goes 1, 2 boxes, 2 boxes, 3. However, on my left side, every little box is worth 1. Is that okay? Yeah, it sure is. Labeling, though, would help the reader. So now let's mark our points. We had, what did we have? So we had a side length of 1, and that gave me a perimeter of 4. Let's mark that. We had a side length of 2, that gave me a perimeter of 8. Let's mark that. Side length of 3, and that gave me a perimeter of 12. Let's mark that. Now, is this linear? Is this, or is it just these points? Well, think about this. This point, does that point exist? Well, let's name the coordinate pair of that point. It would be 2.5, 10, right? Okay. Well, let's think about perimeter equals 4s, right? So P equals 4 times 2.5. We know we have to put that into an improper fraction. So P equals 4 times 5 halves. Do some cross canceling. P is equal to 10. Hey, it works. So is this linear? It is. So I can draw a line. Again, a straighter line, please, with your ruler. But every little point along here exists. All of these points along that line exist impartially. Yes? All right. A little bit more. About maybe 5 minutes. Let's keep it going. Direct variation. In fact, the two equations we've seen are direct variation. Here's the formula. Y equals kx. And direct variation has to do with this k thing, which is called the constant of variation. Let's write that into our notes. And then basically many functions fall into this category. So constant of variation also has concepts of slope. And I know we've talked about slope a little bit as well. So let's think about when we graph direct variation, what happens? One thing we could say is this. It always graphs as a what? Who'd like to fill in the blank? Yes, go ahead. Always graphs as a line. Yeah, you're right. Well done. How about this one? Always goes through the what? Look at the ones we've already done. What have they gone through? Well, if you're thinking origin, you would be right. And that's how they graph. That's how direct variation works. Let's play a little bit with it by talking about something that's its opposite. It's called inverse variation. The inverse variation has its own formula. Y equals k divided by x. And that's going to make a very different situation. When we think about direct variation, that's things like getting coffee. Let's say the coffee costs $3. And so I say y equals 3x. X being the number of cups to buy, and y is the cost. So clearly, if I was going to make a little chart, and I said, well, what if I bought 1 cup of coffee? How much would that cost? It would cost me $3. How about $2? Well, 2 cups. You know how it works. So 1, 3, 2 cups will be 6. 3 cups will be 9, right? Because $3 each. Well, that's direct variation. Inverse variation is very different. Notice how with direct variation, when my input, my x increases, so does my y. Everything increases. Let's check out inverse variation though. What do we use that for? Well, let's say there was a job to be done, and it would take one person, my input, 10 hours to do that job. Well, how long would it take 2 persons? Well, if they're of equal working styles and they take the same breaks, we would say that it would take, I hope you'd guess, 5 hours. Notice how when my input increases, such as 1 person's to 2 persons, my output decreases. And that's how inverse variation works. It goes down, and that's different. And it will graph a lot different too. But let's look at a situation real quick. D equals RT. I know you've seen this before. This is the formula for distance. We know the D represents distance. The R represents a rate. We often call that the speed. And then T is the time. You've done these before. So let's imagine this. Let's say you have a 120-mile trip to go on. We're going to make an XY chart. I'm going to name that the rate is my input and my output is the time. So let's say I went at different rates, different speeds to traverse this 120-mile trip. Maybe I did it several times, and once I drove merely 20 miles per hour. And then how long would that take me? Sorry, let's do it this way. How long would that take me? Well, if I go 20 miles per hour and there's 120 miles, that would clearly take me 6 hours, right? What if I went 30? I'm increasing the input. What would happen? Well, if I went 30 miles an hour for a 120-mile trip, that would take 4. Notice my output, it's decreasing. What about if I went 40? Yeah, you guessed it. It would be 3 hours, right? What about if I went really fast. I went 60 miles per hour for the length of that 120-mile trip. Well, we know it would be 2, right? 2 hours. Well, that's inverse variation. As my input increases, my output is decreasing. Now, let's plug something in here. I just want to look at something. So we're going to use this 26, and we're going to plug it in. So the x is my 20, the k is being divided by the 20, and the y is my 6. Let's set up one more situation. How about this one? So I'll say 3, that's my output, is equal to k, that constant of variation, over 40. Well, what would I do in both situations? On the left, I would multiply both sides by 20. in order to isolate. On the right, I would multiply both sides by 40 in order to isolate. And can you guess what we're going to come up with in both situations? Yeah, we're going to know the K, and the K would be 120. And hey, that was our trip. And you're like, okay, cool enough. Let's keep going. Yeah, let's graph. We're going to graph that. Once again, I need a first quadrant only. It's a real world situation going on. I'm putting the rate as my input. That's why it's on the x-axis, and the time as my output. So we had different values last time. Should we do it again? We should. Let's deal with time first. We know that time went all the way up to 6 hours. So we're going to go every 2 is worth 1. So that would be 2, that's 3, that's 4. I'll mark my 5s just so we're all on track. And there's my 6. Think about the rates. Well, they went kind of in 20s. So I'm going to say that every 2 blocks is worth 10. 10, there's 20, there's 30, there's 40, there's 50. I'll mark 50, and then there's my 60. Oops. Now let's think about what we graphed. We had 26 was one of our coordinates, right? Well, 26 would exist right here. All right, the next one was 34. Go ahead and mark that. Did you mark it here? You should have. Good. Okay. Next one, 43. Yeah, that's where it goes. And then 62. Well, that is not linear at all. In fact, inverse variation graphs in this manner. It looks like this. Arrows on either side. But it's like a curvy thing, yeah? All right, almost done, I promise. Last screen. First, don't worry about the coordinate plane. We're going to deal with that in a second, but I just want to do this all on one screen. Y equals 12 over x. That is clearly inverse variation. We're going to choose some values. This is not a real-world situation, so we're going to choose some negatives too. But let's go with 4 and 3 and 2. Then we'll go some negative 2, negative 3, negative 4. And let's do some plugging in. So we know we're inputting for that x, so we're basically saying 12 divided by 4. We know that's 3. Then we plug in the 3. 12 divided by 3, we know that's 4. 12 divided by 2, we know that's 6. Now some negatives. Now be careful here because that's negative. So it's 12 divided by negative 2. Well, we know that that'll be negative 6. 12 divided by negative 3, negative 4. 12 divided by negative 4, negative 3. You should be able to do that. All right, let's graph the positives. But first, we've got our arrows. Doesn't have to be super huge. You see the range we need. I would like some 5s, though. Always mark those 5s. It's a good idea. It's easy to read. All right, now let's mark 4, 3. Go ahead. Boom. Now, 4, 3. There it is. How about 3, 4? There it is. How about 2, 6? There it is. And you're like, well, I don't really see it. Okay, let's plug in one more. Let's plug in 6. 12 divided by 6 is 2. So let's mark that 6, 2. It'd be right there. And then once again, we got that curvy thing going on. Now let's do the negatives. Check this out. This is kind of cool. So plug in negative 2, negative 6, this one. And that would look like right here. Yeah, you're right. All right. How about negative 3, negative 4? You ready? Boom. How about negative 4, negative 3? You ready? Boom. How about, let's get another. How about if we did negative 6? What would we get? We'd get negative 2, right? Let's do that one. Okay, negative 6, negative 2, boom. And hopefully you can see the similar sort of curvy. And that's what inverse variation looks like in all quadrants, if you will. Wow, this is a long one. Under 19 minutes, I can say. But the good news is you got a whole weekend to think about it. It is Freya's Day. I'm going to take us back to this first screen just to tell you that you know the drill. In investigations, we don't do homework. So enjoy your weekend. I hope you're well. You can reach out to me anytime. Take care. Bye.